This next section, graphing polynomial equations, is pretty short and sweet because we're talking about with what we're given so far, what do we need to do? What do we need in order to draw a graph of a function? To graph a function, what are the pieces you need? The y-intercept. What else? The x-intercepts. What else do you need? That we've talked about so far.
Would you count the half point count the time for
The extrema. Behavior. Oh, we'll talk about that in a second. What else? We have the x-intercept, the y-intercept, the extrema points, the end behavior. Where is increasing, decreasing? Is there anything else we might need? Well, that's a good start. And to be honest with you, this would be great to have. But just by looking at any polynomial of degree n, because if we had this, if we knew the shape and the direction, that would help us also drawing the graph. But we will know basic shape of this graph before we start doing any math. Just by looking at these two numbers. The first one and the very last one. The last one does what for us?
that's our y-intercept.
That's our y-intercept, right? So that tells us where across the y-axis. We know that point automatically. So the other one, this one here, is probably the most important one. It's called the leading term. The leading term is made up of a bunch of information. The number in front is called the leading coefficient. The n is called the degree. Both of these will tell us what the graph's going to look like. Let's talk about end behavior first. When we say end behavior, it says what directions do the graph, or does the graph take at both that's a I call them end intercepts then for lack of better.
But it will be the last section, we determine if they both go over.
Yes, that's yeah, exactly. I forgot we don't talk about that. Yeah, so that's going to tell us the shape of the graph. Is that if our intercepts, if they go up this way, we know at least that much. We also know the y-intercept. So we have a good idea what the graph's going to look like. We also know the maximum number of vertices or extrema. The maximum number of vertices is always the degree minus 1. Think about it. This is an example of x squared. This is an example of x cubed, a cubic function. There's your n, that's your degree. So if your degree is 2, we'll have 1 vertex. 2 minus n is 2. 2 minus 1 is 1. If we have a cubic function, the most vertices we can have is 3 minus 1. We can have 2 vertices. So it gives us another idea of what it looks like. So the shape of the graph is determined by the degree. And the end behavior. The direction is determined by the leading coefficient, A sub n. All right, so let's look at these things. Let's look at an example. Example 1. Here we have h of x is equal to negative 2x to the 4th plus 3x cubed. Graph it. So do we know the y-intercept? It's at 0, 0, right? So we know it goes to the origin. Do we know the x-intercept? So what we have to do here first, let's go ahead and factor. Well, what can we factor out of here? Yeah, there's 3 of them we can take out. Since this one has 4, this one has 3, we can take out 3 of them. Which leaves us with negative 2x plus 3. Again, the degree is the these, remember, what are these called? The multiplicity. I'll show you what they're used for. So now we find our x-intercepts by taking these and set them equal to 0. So our first one, x is equal to 0. Check, got that there. And 2x, so x is equal to 3 over 2, which is 1/2. Okay, so we have the x-intercepts. The y-intercept is at 0. What do we notice about the end behavior? N and a sub n. What is n in our example? The 4. It's the degree. So it's the largest exponent. A sub n is the leading coefficient, which is -2. Since this is even, they point the same direction. Since it's negative, we know the graph will look something like this. Now, is the graph going to be below there, or is it going to be above there? Well, we'll look at the multiplicities. If the multiplicity is odd, then at this x-intercept, it'll cross. At this one's odd, so we know it's going to cross there too. So we know our graph's going to look something like this. Because it's a fourth order equation. It'll have at most 3 vertices. Well, that's all we can tell right there.
They have loads, but it has to have the number.
It can actually, because if the function was just y equals x to the 4th, that graph looks like the squared x squared. Only has 1. So no, it can have, as I said, up to n-1 vertices. Very good question, actually. You don't always have to have n-1 vertices. It's up to that many. So here's our graph. Example 2. F of x is equal to 2x cubed plus x squared minus 8x minus 4. Up until now, we've learned how to factor linear equations and quadratic equations. We haven't talked about cubic functions yet. To find the x-intercepts, we have to factor this equation out. Since it's a cubic, we have 4 terms. We can use something, try grouping. What grouping says is take the first 2 terms and put them in parentheses. Since the middle sign is negative, incorporate that into the second parenthesis. If it was a plus, then we just put the parentheses around the 8x plus minus 4. But since that's minus, we put it in there. So we group those together. The next step, what can we factor out of these two?
Alright. That one.
Separate.
Squared.
X squared, which leaves us
But carry over two over plus one.
right. So to see what goes inside here, whatever you factor out, divide both of these by what you factored out. Because x squared, x cubed over x squared is just x, so it's 2x. X squared over x squared is just 1. Now in the second one, well, since the leading term is negative, we have to factor out the negative. So we take out -4. Remember, we're factoring out a -4, so we divide those by -4. So it's going to be 2x, negative makes it a positive 1. See, that's our goal. We want these to be the same.
So that way.
Pres-
Square minus 4 the other groups.
Exactly. So x squared minus 4 is one parenthesis, and the 2x plus 1 is another parenthesis. So we factor out the 2x plus 1. We can factor out the first one, the x squared minus 4. That's x plus 2, the difference of two squares. But then again, you don't need to, because what you can do here, you can set these equal to 0 and solve. At this point here, to set them equal to 0. So you get x squared minus 4 equals 0, x squared equals 4, so x equals plus or minus 2, which is what this tells us. So x equals -2, x equals 2, and x equals -1/2. Those are my x-intercepts. So the x-intercepts are at -2, 0, 2, 0, and -1/2, 0. The y-intercept is at 0, -4. So we have it at -2. We have an x-intercept. We have at 2 an x-intercept, and at -1/2. So what's the end behavior going to tell us? Opposite directions. And that's positive. So at this end, it goes up, and this end, it goes down. Our y-intercept is at -4. So looking at our graph, does it cross this point or does it bounce off it? So at -2, the multiplicity is 1. Since that's an odd number, it crosses. At -1/2, the multiplicity is 1, so it crosses. And it has to go down to that y-intercept. And we know it has to cross again because it has to be going up. So there's our graph. Pretty straightforward.
If it's even or bounce.
If the multiplicity is a squared or a fourth or a 6, if it's an even integer on the multiplicity, then it bounces. But think about the function x squared. It's at 0 and it bounces. And then here, wherever the vertex is, you know it's increasing here, it's decreasing here, and it's increasing there. Example 3. G of x equals x to the fourth minus 7x cubed plus 12x squared plus 4x minus 16. Next week, I'm going to teach you how we can just solve that, find the x-intercepts, because we'll have at most 4 x-intercepts. But for right now, I will give you the factored form. So the factored form is x plus 1, x minus 2, x minus 2, x minus 4. So what can we tell me about this? What are my x-intercepts? What's my y-intercept?
1, 2, 4.
And my y-intercept? Very good. What about the end behavior?
Oh, sorry.
Both ends are the same since it's 4. Do they go up or down?
Up.
Because it's a positive 1. So we know what we know automatically is from here to here, that's what happens at the endpoints. So since it crosses at -1 and the y-intercept is at 16, it crosses that one. What does it do at +2? Yeah, this one crosses, this one bounces. So it back up here, it bounces off it. And it goes back down. So it looks something like this. So yeah, what they want you to do is, okay, you found the x-intercepts. Pick a number on both sides, plug it into the equation. If it's positive, it's above it. If it's negative, it's below it. And so you know what the graph looks like. Well, we know what the graph looks like because we have our intercepts. We know the end behavior. We know the crosses or bounces. So it saves you so much time. Oh, tons of it, yeah. The last thing in this section is called the intermediate value theorem. It's also called the Bolzano theorem. What it says is this. If I have a function I have some function f of x. On some interval. So f of x is continuous on some interval AB. If f of A and f of B have opposite signs, then they're must be at least one C in the interval AB such that f of C is equal to 0. A lot of words, it means it's a lot easier to look at it in the picture. What it says is this. Here's my function, it's continuous. Here's my interval, AB. The function at A, this is f of A, and the function at B, here's f of B. If they have opposite signs, then we know it crosses at least once at some value C where f of C is equal to 0. That's the intermediate value theorem, the IVT. It doesn't tell us how many or where it is. It just tells us that at least one exists. So let's see how. So basically, all you do is take your function, and plug in A and plug in B, and see what the signs are. Numbers are irrelevant. It's the signs we're looking for. If it's positive, it's above the x-axis. If it's negative, it's below the x-axis. All right, so let's look at some examples here. Use the IVT to determine if f of x has at least one x-intercept. Call a real zero. So here's the first one. X cubed plus x squared minus 6x. On the interval -4, -2. So what this tells us is A is equal to -4 and B is equal to -2. So we have to do f of A and f of B. And according to the intermediate value theorem, if their signs are different, then there's going to be at least one x-intercept between there. So this is f of -4, and this is f of -2. -4 cubed plus -4 squared minus 6 -4. -2 cubed plus -2 squared minus 6 times -2. What's -4 cubed? -64. plus -4 squared is going to be +16. Negative times negative is a positive. 6 times 4 is 24. We have -64. 16 plus 24 is 40. So the answer is -24. On the other side, -2 cubed is -8. 2 squared is 4. -6, -2 is a +12. We have -8 plus 16, which is a +8. So yes, there is at least one x intercept or x real real 0x because their answers are different signs. The same function, x cubed plus x squared minus 6x when a is -1 and b is 3. In other words, it's on the interval -1, 3. So plug those two endpoints inside the equation and work them out. -1 cubed, -1 squared, 6 times -1. So -1 cubed is -1. -1 squared is +1. Negative makes it +6. That equals +6. Now we do the same thing with the -3 or the +3. 3 cubed plus 3 squared minus 6 times 3. 3 cubed is 27. 3 squared is 9. 6 times 3 is -18. So 36 minus 18. We cannot conclude if there exists a real 0 between -1 and 3. Because they're both positive. We can't tell anything. There could be a million of them, but we're just not sure with our numbers.
That'd be the answer. Basically, every time it's the six right numbers.
Yeah, yeah.
They're both.
If they're the same signs, you can't, in intermediate value theorem is not useful. It's only useful if it's negative, or if opposite signs. We'll do one more. So we have 1/3, x to the 4th, minus x to the 3rd. For the interval, -1/2, 1/2. So that's A and that's B. So we have 1/3. Negative, a negative number raised to the fourth, even power is gonna be an even answer. Or a positive answer. So 1 to the 4th power is 1, 2 to the 4th power is 16. Since it's an odd exponent, the answer is going to be odd or negative. We distribute that to both of those. We have 1/48 plus 1/8. We know it's going to be positive. That's all. We don't care what the number it is. It's going to be positive. It's going to be greater than 0. So that's all we care about. And the other one, 1/3 is going to be 1/8 or 16 minus 1/8, 1/48 minus 1/8. Now, because it's a minus sign, we have to get a common denominator. So it's 1/48 minus 6/48, which makes it a negative 5/48. Since they're different signs, yes, there is at least one real 0. Make sense? Okay with that? That's the end of that section.